Hello everyone, thank you for being here. Today I'll present Sharker, a tool I created during this short talk. But first, let me introduce myself. I am Pierre Milioni, I'm a pen tester at Synactive since 2020, and I am now focused mostly on red team engagement. Speaking of which, we've made an observation. Basically, we often ended up with really large packet captures during these type of assessments, and we only had a short amount of time to analyze them, so we often ended up missing valuable data from these captures. So we had to figure out a way to avoid this issue. But first, how do we actually get network captures? As Aurelien said in another presentation, it's quite likely that you can end up in a man-in-the-middle position, either through physical intrusion, as we saw this morning, I think, where you manage to plant a malicious device between the internal network and a workstation. That way, you are able to sniff the traffic going to the internal network. You can also abuse protocols such as ARP, HSRP, or DHCP, pretending to be the router, and so on. That way, you retrieve a lot of traffic. Then you can abuse name resolution protocols, especially in the Windows environments where they often rely on broadcast packets. So that way you can usurp the identity of a specific server, thus retrieving some traffic. And then, less likely to happen, but still, you can create a fake Wi-Fi network. And if you manage to actually make a user connect to that Wi-Fi, you can provide him with a gateway, and then you can sniff the traffic. Other possible scenario, you manage to compromise a network equipment. So during your intrusion, you end up on a router, either through features of this router or because you have a shell on the machine, you can start sniffing traffic. Or that happened if you browse the file system of a server of administrator workstation, you may end up on pickup captures. So all these things may lead to the compromise of sensitive data. So yeah, why? Why would we find sensitive data? Because everything should be encrypted, right? Well, not really. There are several protocols widely used that remain insecure. In internal network, especially, we find lots of legacy protocols still in use. Quick example, NTLM and Kerberos, especially NTLM and Kerberos when there isn't Kerberos armoring enforced, could lead to the compromise of credentials. You can also identify authenticated HTTP proxies that could lead to the compromise of credentials. You can also find files transiting through unencrypted SMB. So these things can be retrieved by a simple packet capture. And then you can improve your knowledge about the internal network through the discoveries protocols such as ARP, DHCP, and DNS. So now the tool, Sharker. The idea behind this tool is to have something simple, reliable, and reasonably fast to parse these PCAPs. And we did not find these three things in the already existing ecosystem. Basically, some example, pcreds, probably the most widely known, is quite difficult to extend since it relies on SCAPI and manual parsing of packets. It's quite tedious to actually implement new filters. There is CredSlayer, which is quite similar to Sharker, as we'll see. However, it remains slow on larger pickups, so not really usable in that case. And then there are other tools such as Network Miner. However, it's designed to run on Windows, so it's quite complex to use it on Linux. And there are multiple others that are either too complex, provide lots of features that we don't really need, or are shipped with lots of dependencies, things that we don't really want when we are treating sensitive data. Now, the design of Sharker. Basically, we use the T-Shark tool. So T-Shark is the CLI of Wireshark for packet parsing. Why T-Shark? Well, Wireshark was released in July 1998, so I was basically 1 year old at that point. So I figured they would have done the parsing way better than I would ever do. So let's just reuse their work. And they already made tons of dissectors. Basically, if you go on their GitHub page in the dissectors part, there are more than 1,000 files, so you cannot even display all the files there. So yeah, let's just reuse their work. So Sharker, as we've seen in another presentation, I was like, okay, it's going to take me an hour or two and I'll be done. This will be a simple tool. So it started as a simple bash script. And then I started to run T-Shark once to retrieve the user agents, and then run it a second time to retrieve the Kerberos hashes. But I cannot compute the hashes directly with T-Shark, so I have to do some set shenanigans to end up with a proper hash, and so on and so on. And in the end, it was really complex doing it that way, and super slow, since we had to parse the capture each time for each thing that we want to extract. So I started again, switched to Python. Why Python? Because it's easy to understand, easy to develop. I wanted people to just understand the code if they read it. That way, we run T-Shark only once. So we do only a single pass. So it starts to complexify a little bit because we have to select the packets correctly. And we leverage the JSON output of T-Shark. So the dash T JSON that yields JSON representation of all the packets that matches our selection. In particular, the dash capital Y allows us to filter the packets that will be generated in JSON afterwards. So this allows to really early on discard packets that are not valuable, which allows us to gain a lot of time during the parsing operations. So this is an example of an SMB2 exchange and within an NTLM authentication. So it's really easy to retrieve all the different values, and the keys are self-explanatory. So still design, I wanted it to go really fast, so I started with a multiprocess app because I knew that threading would cause problem in Python. However, it remained complex and not that fast actually, because I was sharing the object, lots of objects through all the processes, which took time because of the serialization, deserialization, and so on. So it was not that smart actually. So I switched to a multi-threaded app. I really wanted to go fast, so I needed more threads. However, it remains still complex due to the different queues, and not that fast, probably due to the global interpreter lock. So yeah, I finally switched to a solution I should have started with, meaning a single process and almost single-threaded app. It yielded the best results among all the solutions, simply because all the hard work is done by T-Shark. It's T-Shark that parses the raw packets and transforms them in JSON. We only are doing quick computation on keys in a JSON, so it goes fast. It's not really CPU bound. So I should have started with that and kept it simple. Now, when we get the JSON representation of a packet, what could we do? Well, Sharker implements filters as Python classes. So this is a simple case. We want to extract the DNS requests performed in the capture. So this is the complete example that does that. Basically, you create a new Python module, you implement a new class, you create a new class, give it a name, a description, some categories, so that the users will be able to filter on later. The heavy keywords prevents Sharker running the filter by default, so this can, as we'll see later, affect the parsing time a lot. And then you specify a pickup filter attribute. So this is the attribute that allows T-Shark, so the one generating JSON output of packet, to early discard unwanted packets. So this is where you define the filter that defines valuable packets. And then you have the mandatory selectors that just allows Sharker to select what keys you want to export or display in the console. That's automatic. Now, a more complex example. If you want to extract the NTLM authentication hashes, you need something that stays along the whole parsing of the capture to save the NTLM challenges that are in the second NTLM authentication message. And then you implement a parser function. And in that parser function, you will check whether it is the second or third NTLM message. If it's the second, you'll store the challenge in the object variable defined in the init function. And if it's the third message, you just start generating the hash, select the proper challenge from the variable, and then you call the output function. Sharker will automatically either display it in the console or write it to file, or both, actually. Now, on to limitations. Basically, Sharker highly relies on T-Shark. So if T-Shark cannot parse a packet, Sharker won't be able to do anything about it. It's definitely not built for exhaustive analysis, meaning that if you really want to dig deep in a capture, you're better off using Wireshark manually. And if everything is encrypted, or like you're seeing only VPN traffic, obviously you won't be able to do anything about it. Quick example of what it looks like. So you just call Sharker. The -C option allows you to filter on categories what you want, what you don't want. -U to have unique output, and then specify the output, and you get all the hashes there. So obviously these values are placeholders. Now, some comparisons with the other tools. So 4 different captures taken from 4 different engagements. As you can see, for Sharker, pcreds, and credslayer, the timings are for the whole parsing and analysis, while for T-Shark, it's only for the generation of the JSON output. So we compare pretty well to the others. And as you may notice, there is a huge gap between the 1 gigabyte capture and the 700 megabytes capture. 700 megabytes capture being that needs way longer time to parse. This is due to the fact that the 1 gigabyte capture only contains contains lots of packets that are not useful, so we can discard them really, really early on and gain a lot of time. So that's why on the 1 gigabyte capture, we are really fast compared to the others. Yeah. Now, quickly, what do you do from there? Well, you can start brute forcing offline hashes that was generated. You can start relaying authentication, especially on MS SQL Server, unless there is a channel binding. Then you can start abusing protocols that you identified. You can improve your knowledge about the network. It's really up to your imagination at that point. Now, from the defensive point of view, what could we do about it? Well, it's quite complicated. Once the attackers are already in the LAN, try to eliminate legacy protocols as much as possible, enforce encryption when possible. Definitely use strong passwords that resist offline brute force attacks or directory, word list attacks, and try to move towards zero trust models in a way that you don't really have a LAN anymore. So yeah, it's quite complicated. Well, thank you very much. If you have any question, I'm here. The QR code and the link both leads to the tool that has been released yesterday, actually.
No, I forget it.
Will you be attempting another multi-threaded version now that the global interpreter lock is gone from modern Python versions?
Can you repeat the question?
Yeah, sure. So will you be attempting another multi-threaded version now that the global interpreter lock is gone from modern Python versions?
For now, not really, since it's working well that way. However, if we start to have lots of filters that do more computing, more computation, maybe we'll switch back to something like this to speed up things. But for now, it's working quite well, so not really needed.
All right, thank you.
I just wanted to know how much time did it take for making this tool?
Well, more time than I thought. Basically, there were several iterations before I reached the final version. I believe we're talking about, I don't know, 10, 20 hours, something like that. So it's still a small tool in a way, but I kept refining it just to find the sweet spot where it's still simple enough so that you can tweak it, but fast and usable enough so that you can run it during engagements. And I wanted it to be able to run on live interfaces and on weak machines like Raspberry Pi, because specifically during physical intrusion, you may end up needing such a feature. So yeah.
Okay. So do you plan to have new features on it, like new systems?
Yeah. For now, there are the basic filters that are implemented in the other tools. We have several ideas in mind. Specifically, we want to do some passive reconnaissance a bit more. So like from the packet capture, you are able to know if a server is enforcing signing, SMB signing, for instance, and we want to be able to display that to the user as well. So we have ideas. If you have ideas, do not hesitate to create issues on the GitHub repo, or even better, to contribute to the tool. Everything will be looked at.
Will you do a pull request on Wireshark to integrate the stuff directly?
No, because this is really an independent tool. So we are running T-Shark, the Wireshark CLI, but it's really independent. We are just retrieving the output of this and parsing it. So there is no point in integrating it directly in Wireshark.